Okay, we are in business. Last time, we just barely started with section 2.4. So let me just remind you what we talked about. We talked about this thing called D, right? It's not to be conflated with DF, right? DF being a function that takes input vectors to output vectors. D is the operation that kind of creates DF. It's the process of taking a function and creating the resulting derivative matrix. And the statement that's being made here, the much more non-trivial, much more substantial statement, is to say that D is linear. Again, in other words, that if you take a linear combination of functions and find its derivative matrix, you get the linear combination, that same linear combination of the individual derivative matrices. So we talked about this last time, did an example that I won't repeat, but one other quick thing to point out is that there also, D has a product rule and a quotient rule. Actually, it has a couple of different product rules, depending on whether the functions are both vectors or scalar and vector, etc. So make sure to look and read that stuff in the book. Again, I remind you I have to make tough choices about what to actually spend class time on among the fair game material. And so this discussion doesn't quite make the cut for class time, but it is fair game. It is part of the course. So make sure that you see and read and retain all that stuff. Okay, so moving along. So higher order partials. So this is actually a lot like single variable higher order partials. We make the observation in single variable calculus. If you have a function of x and you take its derivative, well, the derivative is also a function of x. So on that basis, you can take its derivative, etc. So same deal with a multivariable function. If you have a function of several variables, so is its partial with respect to any one of them. Also a function of those same several variables. So just as a for example, here's a function of x and y. You can take its x or y partials. But now let's take a look at, for example, its x partial. Its x partial, you can see it right there, also a function of x and y. So I can take its x or y partial. And likewise for the y partial, etc. Okay. All right. Now let's talk about the notation for these higher order partials. Awkwardly, if you have the x partial that I've already computed there, and if you then take the y partial of it, all right, the way that gets denoted in practice, the way we represent this is with this notation right here. And I find this a little, just a little bit uncomfortable, because what we're doing is we're seeing that there's a partial symbol and another partial symbol, and so we just write partial squared. Just be clear. Partial, that little partial symbol, it's not like that's a number that I'm multiplying by itself, right? This is kind of an abuse of notation when we write partial squared. This is just a recognition that there's a kind of two of those in the numerator. That's all it is, and it's nothing to worry about. It used to bother me a lot when I was younger. Also, notice what we have down here is just a sort of a compilation of, well, we've got a partial y and a partial x. And I think it's appropriate and reasonable. We do need to worry about the order. We're talking about the x partial of the y partial, or the y partial of the x partial. So make sure to preserve the order there. Okay. Okay, now here's an alternative way to do it, though. So keep in mind, if we have an x partial and we take a y partial of it, well, this is an alternative notation for the x partial, and here is that equivalent notation for taking the y partial of it. And notice, also awkwardly, look at the x and the y. If I keep those in the same order, it kind of seems backwards, right? So if you just, let's pay careful attention to which one's where. We have the x partial on the right in the above notation, but it's on the left here. And the y partial is on the left up here, but it's on the right over there. So all I can tell you about this is just a consequence of our notational conventions that have been around for so long, we can't just change them. All right, so we're stuck with this. The way to keep this straight is to remember how these notations suggest taking derivatives. The one where you put the derivative notation on the right-hand side, progressive derivatives proceed further to the right, as one would expect. This one up here, where we put the derivative notation on the left of the function itself, well, further derivatives proceed to the left, not the right. So it makes sense. I mean, it's given our notational norms, we kind of have to do this, right? But it remains that they do look backwards, and it is an opportunity to accidentally make mistakes, and so please do be careful about that. Okay, now you'll notice over here on the right side, I have computed also the x partial of the y partial, in addition to here the y partial of the x partial. And notice in this case we got the same answer. Weird. Or is it? It turns out it's actually not that weird. It's not that unusual. For a very large category of functions, this always works. Not for every function, but for a very large category. And that category is what I'm going to talk about next. We're going to talk about this thing called CK. So the K here refers to how many partials do I have to be able to compute? And furthermore, the C here denotes that they also have to be continuous. So C2, for example, the 2 being an indication that I need to include up to and including all the second order partials. And if it was a 3, it'd be all the third order partials, etc. And it does have to be all of them. So this is a very common vector space to talk about. CK, pretty standard thing in math. You're going to see this kind of thing substantially in Math 353 next semester as well. But here we're going to use it as follows. If you're talking about functions in this category that are this nice, where all of their kth order partials not only exist, but they're all continuous. That nice of a function, then up to the kth order partials, the order that you take the partials doesn't matter. So just a neat fact, and I'm not going to prove that here. The proof of this is much more, it's quite a bit beyond the scope of this course. Okay. All right. So let's talk about what these look like geometrically. We're going to start with the unmixed partials. Let's start with, for example, FYY, let's say. What does that look like geometrically? Do notice, and I remind you, I know I say this a lot, but I say it a lot because it's really important. You always have to keep in mind what your geometric context is, right? So here, we're going to talk about what they look like on graphs specifically. The interpretations we're about to make here apply only if you're looking at a graph. Right? And of course, everything changes. If you're drawing different pictures, you get different interpretations. Okay, on the graph context, let's think about how I compute FYY. Well, the first thing I do is I hold x constant, and then notice I continue to hold x constant for both of the derivatives. So another way to say this is the step 1, I hold x constant. In other words, I take this cross-section and look just at the cross-section in that, that didn't go out well, just at this cross-section in that constant value of x plane. And in that plane where x is constant, what do? I take a derivative and then I take another derivative. It's just a plain old second derivative with respect to the only variable, y. It's the only variable because x is constant. So it's literally a second derivative of a single variable function, and we have a pre-existing interpretation of second derivatives of single variable functions, and that is if it's concave up, as in this picture, then that second partial is positive, and vice versa. Is that cool? All right, now let's talk through what's the deal if we are looking at fxx. Well, that means that x is our variable. That means we hold y constant. And again, it's the same derivative for both of the derivatives. So y is going to be held constant, and it's going to stay constant. Why did I do that in green? Let me do this in gray. Sorry. We're going to set it constant and keep it constant. And that cross-section will be some curve. And fxx means we're literally going to take the second derivative of that, again, still single variable function. X is the only variable if y is held constant. And again, second derivatives, single variable functions. We already know the deal there. If, as in this drawing, it's concave down, that means that second partial is negative. Is everybody happy? All right. So now notice, in this Pringle graph is a pretty good example of this. These don't have to be related to each other. One could be positive, the other could be negative. No problem. Okay. All right. Okay. Now here's where it gets a little tricky. What if we are talking about a mixed second partial? What's hard about this is I can't just say, oh, hey, check it out. Look, one of the variables is constant for the whole calculation. I can't do that because it's not true. For the first part of the calculation, x is constant. But then after that, x is the variable and y is constant. So, and vice versa. So you can't just say, oh, this is morally a single variable calculus problem. It's not. So what we're going to have to do is kind of go back to first principles and think about what these things mean as I go in the process of calculating this. What does it look like? And then make our interpretation from that. So here we go, starting with the y partials. Y partial says slope of the tangent line to the graph. So again, we're looking on the graph context, and so if I'm at a point, let's say there, and I want to talk about what does the y partial look like on this picture. Well, I look in the y direction, and in that y direction, I look for the tangent line to the graph. It's going to be some line like that, and slope of that graph is what that y partial is. Now, I should note I did not draw a surface here. I find that it just kind of makes the picture awkward and hard to draw, and it basically doesn't help. So use your imagination to imagine a surface for which that's the tangent line in question. Okay. All right, now how are we going to get our hands on this part, the fact that I need the x partial of the y partial? Now let me first dispel a temptation. It's tempting to say, oh, x partial, isn't that like the slope in the x direction? And the thing is, it's the slope if you're looking at the graph of its object, right? The thing we're taking the x partial of. Are we looking at a graph of partial of f with respect to y? No, we're not. This is a graph of f. We do not have a graph of the partial of f with respect to y. So I can't use a graph interpretation of this x partial because I'm not looking at a graph of the thing I'm taking the partial of. So I've got to take a different point of view, and the point of view I'm going to suggest is that we think about the fact that x partials means how does the object, whatever we're taking the x partial of, how does it change as you move in the x direction? Right? So as I move that way, how do these tangent line slopes change? So what I've got to do then is draw a few more examples of y partials back here as I move in the y direction. Let's suppose that's what that tangent line looks like. Over here, as I move in the y direction, maybe the tangent line is like that, et cetera, et cetera. One could imagine various different tangent lines in the y direction as I move in the x direction. And now keeping in mind that each one of these tangent lines up here gives me a slope. Right? This one's like -2. This one's like -1. This one's like, -0.5. This one's about 0. This one's about +0.5. Right? So what is happening to these slopes as I come out of the page toward y'all, right? As we move in the x direction, these slopes are, they're going from negative to positive. They're getting bigger. they're increasing. Right? So what we've got here, whatever it is that we feel like we're seeing there, that's what this mixed second partial represents. And I'll tell you what I think I'm seeing, and this is just kind of the way I like to think of it, and I wish I had a good visual aid. I have not been able to think of a way to do this. What I really need is a sheet of very flexible, bendy rubber that's about this big. And if I were to be able to imagine I had such a sheet of rubber and I grab it on the corners, right, all four corners. Well, I would need to twist it, right? And the back, I would need to twist this way because on the back end it's kind of the left side that's kicking up. But on the front side, I need to twist the other way because it's the right side that's kind of coming up. So it would be literally twisting the sheet. So that's a point of view on what these mixed second partials represent. They measure a twisting of the graph. And the word they throw at this is called torsion for whatever that's worth. But anyway, it's a harder story, right? Visualizing these mixed second partials, a little bit tougher than previous sort of things you've seen. All right, how are we doing? Yes.
For the outer partial, the one above.
Yep.
So we're saying that the slope is becoming less negative.
Well, I'm saying that as let's see your colors. As I move in that x direction, these y slopes, the things that the x partial is keeping track of, these y slopes are becoming less negative and then eventually, in fact, positive.
But
Yes.
Is that out of the page? Isn't that just on the dy plane?
Well, so these cross sections are parallel to the YZ plane. Right, that's right. But what I need to do is keep track of how those cross section slopes change as I come out of the page. So here's kind of a movie of that process. Imagine my forearm is the cross section, the tangent line to the cross section, right? So as I come out of the page, it's doing like this. Back into the page like this, out of the page like that. Does that make sense? Yeah. And so you can see there's a kind of a twisting to the motion. Yeah. Okay. Cool. All right. Okay, now that finishes section 2.4. We are going to jump real quick up to chapter 3. I'm going to do just section 3.1. The reason for this is before I get into section 2.5 on the chain rule, which we'll get to in a few minutes, I want to be able to take a certain point of view on the chain rule. And the point of view that I want to take is in terms of interpreting derivatives as velocities. And the book hasn't really done that yet, and they don't really get around to it until 3.1. Well, I'd like to be able to take that point of view earlier with the chain rule. And so here we are. We're going to do 3.1 first, and then we'll go back to 2.5. So, okay, here we go. Taking derivatives of parametric curves. Y'all remember parametric curves, right? Position is a function of time. Okay. So let's talk about what a derivative of such a function would look like. Keep in mind a derivative is a matrix. Notice there is only one input variable. Well, in the derivative matrix, input variables correspond to columns. So if there is only one input variable, that means my derivative matrix only has one column. Okay. Furthermore, wait a second, aren't these supposed to be partial derivatives? Well, here's the thing. There are no other variables to hold constant. There was only one variable in the first place. So these are, in fact, just plain old, good old single variable derivatives. Here. And I'm going to make the case in a moment that this vector of derivatives is actually the derivative of the vector valued parametric curve position function itself. Said differently, what this says here is that you can take these single variable time derivatives one component at a time. Right? You can do them component wise, call it. So why is that? Why does this single variable derivative, and this right here is our good old math 111L single variable derivative. Why does that compute one component at a time, or all components are computed separately? Well, you just look at the elements of it. We're subtracting vectors. How do we subtract vectors? Well, one coordinate at a time. How do we divide a vector by a scalar? One coordinate at a time. Right? And we've skipped over the discussion of limits, but I'm going to assert, I think plausibly, that limits can be computed one component at a time. And let me just sweep that under the rug. It's not something we need to worry about. So, nice punchline though. Yeah, the derivative of a vector is just the vector of individual coordinate derivatives. Yes?
Would you say then that the only really key difference to note between single variable position and acceleration and velocity acceleration and multivariable is just to note that this is going to be a vector valued function? Yeah,
I'd quibble with your language a little bit. So you said single variable versus multivariable. This is all single variable, right? But I think the distinction you're drawing is between vector valued functions versus scalar valued functions or real valued functions. Yeah, but find and replace that point on what you just said, and yes, absolutely. The main difference between derivatives of parametric curves and derivatives of just scalar valued functions interpreted again as position, but just along the x-axis. And it's all pretty much the same stuff. It's just vector. You could think of it this way: that when you're doing single variable, you're driving along a road and keeping track of your position as you drive along the road, think of those are just one-dimensional vectors. Yeah, totally. Okay. Yep, totally. Okay, so what does it mean? And y'all might see the writing on the wall here already because of the analogy that we just talked about. But it's going to turn out that velocity is what the derivative is. And let's see why that is. Now we've got to actually, talk through this construction and one step at a time and maintain, pictures of what we're talking about as we go. I warn you, though, it is very tempting. And I know I say this a lot, right? But you got to keep track of what kind of a picture we're looking at. Very importantly, when you're doing a parametric curve, the picture that you use to represent the parametric curve, usually not the graph. You're usually just looking in the target only. And it's just not a graph, right? It's there is no t-axis when you draw a parametric curve, typically. You just draw the path that the curve follows. So anything that you think you know about single variable derivatives in terms of, single variable derivatives are slopes. Only if you're looking at a graph. We're not looking at a graph here. So you got to toss that interpretation out the window. This is not a graph. We're not going to get slope. That's our answer. Okay, so let's walk through it. We have a point x of t. Then we have a little bit down the road, h seconds later, we're at this point on the curve. And then let's look at the difference. This numerator, that difference is this vector. And then when we divide by h, right, we're going to get a vector. Let's see here. Let me color code this a little better. Having divided by h, let me color that. We're going to have that same green vector, but just a little smaller, as I've divided by whatever h is. So there you go. And one thing you're going to notice right off the bat is that this thing we're taking a limit of, and let's get rid of all this other stuff, this thing that we're taking a limit of points in the same direction as this secant line. You may remember that terminology from Calc 1. A secant line is a line that goes between 2 points on a curve. Right? So, all right, now what happens as I take the limit? Well, taking the limit as h approaches 0, this point over here is going to get successively further and further toward the original point. This direction, then, that secant line direction is going to be just a little bit closer every time, a little bit closer to eventually being, final result, the tangent line to that curve. Now I emphasize, again, you hear tangent line and you think, just like in single variable. Okay, well that part, yes, it is. There is a tangent line, but again, not the graph. Not the slope. We're not talking about the slope of this tangent line. All we're concluding is that the eventual direction, the direction that the derivative points, that direction is the direction that the particle is moving. It's the direction of motion. It's the direction the curve is going. Tangent line direction. Is everybody with me? Okay. Right. Okay, next question. What's the magnitude of this vector? And here, and again, let's not get lost in formalities here, but this vector, its magnitude, well, it's just that distance. And this denominator represents an elapsed time between time t and time t plus h. So if you look at the magnitude of this thing, right, the magnitude is pretty literally distance per unit time, otherwise known as speed. So altogether then, this is a pretty satisfying result. What we have is that this thing we're trying to understand, this derivative of a parametric curve, it's a vector that points in the direction of motion whose magnitude is equal to the speed. It's the velocity, our pre-existing physical concept of velocity. So that's a really, really useful fact. Derivatives of parametric curves give you velocity. And then likewise, we define the second derivative, namely the derivative of the first derivative. The derivative of the velocity is acceleration. Okay, so yes, just like in single variable calculus, totally. In fact, this next example is going to remind you all pretty substantially of some single variable calculus examples. So here we go. We've got a velocity given to us, and we've got a starting point. At t equals 0, we know where we are. And let's two things. First, let's find the acceleration, and then second, let's find the position function. Okay, well, acceleration. Acceleration is the derivative of the velocity, and I know the velocity. So all I have to do is just take the derivative of that velocity, and a little bit of easy calculus, boom, we win. Everybody happy? Notice I took these derivatives one coordinate at a time, right? So the derivative of this is that, and the derivative of this is that. Again, derivatives of vector-valued functions, you can just do one coordinate at a time. Cool. All right, now, here's where it gets a little trickier. Let's find x. X is the antiderivative of velocity, because velocity is the derivative of position. So I'm going to have to take the antiderivative of velocity. Now, again, I know velocity. Here it is. Velocity is all of this business here, so I'm going to take an antiderivative of that velocity. Again, for the same reason that we take derivatives one coordinate at a time, we take antiderivatives one coordinate at a time. So I can compute these antiderivatives just, first coordinate first, second coordinate second, whatever. I am going to take this opportunity to remind you, that you should be proficient with all of the Calc 2 anti-differentiation tricks and rules and facts and all that stuff. And I know it's a lot, but this is in the prerequisite trail of this course, and hopefully no surprise, you can't do multivariable calculus without single variable calculus. So this kind of thing is going to come up a lot and in other contexts as well. So make sure you're good at, the standard antiderivative, functions you just have to know, like the antiderivative of secant squared, right? You just have to remember that that's tan, right? Make sure you're good with the integration by parts, and make sure you're good at substitutions. And then also, don't forget, there's a bunch of stuff like, trig integrals. Like, how do you take the antiderivative of sine squared times cosine cubed? There's a trick to it. So you got to just remember all the little tricks, and it's annoying, and I know, and I sympathize, but that stuff just doesn't go away. All right, so that said, don't forget your plus C, and you have to have the plus C in here, because remember, everything that I've got written down here, no matter what C you put there, is a perfectly acceptable antiderivative because, after all, any one of these things, when you take the derivative, will all give you the same velocity, because when you take that derivative, the constant goes away. So all of these things, no matter what the C, all are antiderivatives. You can't just write one down that you like best randomly, effectively, right? So we have to write all of the antiderivatives down and then figure out after the fact which one, namely solve for my integration constant, which one is actually the right one. Okay, so here we go. Y'all may remember this process. Notice we have additional free information about what happens when t equals 0. So I'm going to plug in t equals 0. That tells me, for one thing, that position is 5, 6. All right, and I can plug in the same t equals 0 into here, and that tells me that this business is 3, 1. Right, and then of course our integration constant comes along for the ride. Nothing happens there. And so our original equation, in which I don't immediately know what C is, when I plug in t equals 0, the equation turns into this equation. And this one is easy to solve for C. You can just kind of subtract that one term over, solve for C, and C is 2, 5. What do you think? Is everybody okay with that? Heads up. Notice the integration constant and the initial value usually not equal. I mean, after all, why would they be? Why would this equal to that? Right? They're usually not the same thing. Because, of course, this thing right here, which comes from this thing right here, usually not just all zeros. Now, there is an illusion that a lot of students have been, victimized by, and that is in a lot of high school classes. A lot of high school classes, they'll only give you like velocity functions that are polynomials. I think they're trying to be nice, right? Because polynomials are easier to take antiderivatives of. And here's the thing: if these are nothing but polynomials, then what we have here in blue would be exclusively polynomials with at least one factor of t, which then when you plug in t equals 0 would make this always 0, and that makes it look like these should always be equal. But that's an illusion. It's a coincidence. And in practice, in the real world, it's usually not true. Right? So please do be careful about that. Don't make the mistake of thinking that the integration constant will always be your initial value. And by the way, even if the algebra happens to work out that way, I remind you there's a difference between a right answer versus valid reasoning. And if your reasoning is the constant is always equal to the integration, always equal to the initial value, even if it's the right answer, that as reasoning is absolutely false. So you got to make sure to do this process. Show me the reasoning that gets you to your integration constant. Okay, all right, enough of that. Okay, so real quick, there's a bunch of other stuff in 3.1, what I'm going to loosely call the Kepler stuff, a bunch of stuff about planetary motion and this kind of thing. And it's, it's cool in its ways, but it's not part of the course, and you're not responsible for it. If you want to look at it for just kind of historical, cultural interest, go ahead. But it's not part of the course. You're not responsible for it. That said, there is one little bit in there that is fair game. It is important, and you are responsible for it. So that is these two formulas right here. They're sort of product rules, if you will, for vector valued, single variable derivatives of vector valued functions. And we have a dot product rule, and a cross product rule. So notice these as product rules look exactly like you would hope, right? So this is good news, right? Nevertheless, there are statements that look like they ought to be true but aren't. And so when we find statements that look like they should be true but actually are, it's worth noting. Okay, so cool. Alrighty. So that was our little jaunt into Chapter 3. We're now going to jump back down to Section 2.5. It gives me the tool that I really wanted, namely I wanted to be able to view single variable derivatives as velocities. And so here we go. Reminder from single variable calculus. If you have an input velocity in the x-axis resulting in an output velocity on the y-axis, there's a relationship between the input velocity and the output velocity. Notice, by the way, using the derivative to represent a velocity, thus our jaunt to Chapter 3. The relationship between the input velocity and the output velocity is the derivative. Okay, so this is a point of view on derivatives. There are other points of view, of course. This is the one that I think is going to be most useful for what we're doing here. So So in particular, it's a factor. The way that a derivative relates input and output velocities is that it is the factor that you multiply by the one to get the other. Is that cool? Everybody's happy? So probably not on your top 3 list of favorite points of view of single variable derivatives, but this is the one we need to take here. So what we're going to do is apply this to this composition of 2 single variable functions. And by the way, this whole page is about single variable calculus, which I know you know, but again, I'm trying to set up a pattern for easy extension to multivariable. Okay, so here, y is a function of x. And here is the corresponding statement about input and output derivatives. Input and output velocities being related by the derivative of f. Okay, next. Here is a subsequent single variable function. I say subsequent because the output from f is the input to g. Right? So z is g of y. And now, different letters of the alphabet, yeah, sure, but same exact interpretation here. Notice this says input velocity, y prime, output velocity, z prime, are related by the derivative of that g function. So, same deal. And then likewise, the composition. Now keep in mind, if you have a function that then feeds into another function, all together, z viewed as a composition function of x, same deal. We have an input, we have an output, and I can talk about input velocity and output velocity being related by the derivative. Okay, so with those all noted, here's the tricky move. What I'm going to do here is I'm going to take this formula for y prime, and I'm going to plug it into here, and that turns equation 2 into this, which I can rewrite as that. Now, all I did is I just plugged in this formula for y prime into here and recopied and rewrote. And having done that, now let me compare these 2 equations. And notice, in both cases, we've got z prime being something multiplied by x prime. So these 2 somethings must be equal. So that and that must be equal. Is that cool? Now this is how you'd write it down algebraically, but let me tell you the same story again, but a little bit more sort of like intuitive convenience. Let me come back up here to our first thing. Think of this transition from the input space to the output space, turning the input velocity into the output velocity. It's just multiplication by a factor, right? And so if you think about it then, looking at this part of the picture, the velocity that we start with, well, we multiply it by a factor as part of f, and then we multiply that by a factor as part of g. So what happens when you multiply by a factor and then a second factor? And I claim that, well, altogether you've multiplied by the product of those 2 factors. right? That's just how multiplication works. And ultimately, that's what the chain rule is saying, is that if you multiply by a factor, and then after that you multiply by another factor, grand total you have multiplied by the product of those two factors. That's just a different point of view. Okay, so that said, differentiation turns a composition, right? Z as a function of X as a composition, into a product, namely the product of the individual derivatives. So, it's a pithy, rolls off the tongue way of thinking about the chain rule. Okay, all that is review, single variable calculus. It sets up, though, a pattern, and what I'm going to do now is I'm going to do the exact same thing to multivariable. I mean, it's the same strategy. Step 1, interpret derivatives as being relationships between input velocities and output velocities. Namely, the derivative is a factor that you multiply by the input velocity to get the output velocity. So now this is just, we've got vectors here now instead of scalars, right? They're two-dimensional spaces instead of one. They could be three-dimensional or five-dimensional, whatever. But still, the derivative is the thing you multiply by the input to get the output. And okay, sure, it's a matrix. Okay, with that point of view, again, let's look at a composition. F. Here's that point of view applied to F. Derivative multiplies by input velocity to give output velocity. Now let's look at the subsequent function that the first one composes into. Here, Z's are functions of the Y's. And here's that same statement again. The derivative multiplies by input velocities to give output velocities. Now applied, though, again to the second function. And then the composition. This statement up here, labeled 3. The derivative is what you multiply by the input velocity to get the output velocity. Right? Same story. Different. Looking at the composition function. Okay. So again, 3 equations. Again, I mean, you can look. I deliberately laid it out on the page. You see, the layout on the page looks just like this layout on the page. It's just that now these are vector spaces and such. But look at what happens if I again take this as a formula for y prime, plug it into there. Whoops. The blue equation then turns into this, aka this. That's just plugging in. And now if I compare these two equations, again, z prime is something multiplied by x prime, and so these two somethings must be equal. Right, so that sort of review, that discussion of single variable chain rule, again, not because I didn't think you knew it, I knew you knew it, but I wanted to set up the pattern that we can then shamelessly steal to get an approach for understanding the multivariable chain rule. And here it is, our multivariable chain rule now is this statement about products of matrices. And notice it rolls off the tongue in exactly the same way. Differentiation turns a composition into a product, this time a matrix product. Is that cool? Everybody happy? Okay. So ultimately, again, I like to point out this is really not that big a deal. If you think about things from a vector's point of view, how do I turn this vector into that vector? Well, multiply by the df. And then once I have that, how do I then further turn that into this? Well, multiply by dg. So altogether, if you want to turn x prime into z prime, namely if you want the derivative of the composition, well, first multiply by df and then multiply by dg. And that's exactly what this says right here. And let me, again, annotate. If you're looking at a function that first does F, and then second, that doesn't, let me do this in the pencil mode, sorry. F acts first, and then G acts second. Well, then what you're going to do to X prime, right? In other words, to what these matrices act on, what you're going to do is first multiply by the DF matrix, which gives you Y prime, and then that you will then multiply by DG to get Z prime. So again, it's just a two-step process, and these matrices do the two steps, and altogether, that's what the combination is. Okay. All right. A couple of things to say about this. Do be very careful about the order. I know this is super annoying, but you notice how F is on the left here, but it's on the right in the, actually, you know what, let me come up here. It's on the right in the composition. G acts second. It's on the right in the diagram. It's on the left in the composition. This is a relic of notation. Somebody decided hundreds of years ago, I don't even know how long ago, that if we have something and we apply a function to it, we'll put the function to the left of the thing that we're applying it to. And so subsequent functions go further to the left. Whereas when you compose, and when you're drawing a diagram, right, the kind of the usual convention, at least in the U.S., is that diagrams kind of proceed to the right. And so this is just, the conventions are incompatible with each other. And if I had a time machine and could, go back to the moment that this got decided, I would go back and fix it. But we can't. So we just have to be eternally vigilant. I encourage you not to think in terms of left and right. It's going to be too hard to keep that straight. Don't think in terms of left and right. Think in terms of acting first and acting second. And you just have to remember that in this notation here, whatever is on the right acts first. And in diagrams, it's what's on the left that acts first. And just, always translate accordingly. Okay. Questions before we go on? Okay, so one other thing I should say real quick. Two other things I should say real quick. Okay, let's see here. First, I will talk about dimension. What would change if there were a third y variable, so that this intermediate space was, in fact, three-dimensional? How would that change this argument? And I claim it would not change a single thing in what's written on the page. In fact, it would still be input velocity, output velocity. Now, the output velocity is now a three-dimensional vector. Yeah, sure, fair, right? Fine. But it remains that df is the matrix that multiplies by the one to get to the other. The shape of the df matrix does change, absolutely, but my notation for it doesn't. And that's what's really nice about you don't want to get bogged down in partial derivatives, right? Because that's treating what are fundamentally vectors in terms of their coordinates, which is just, it's not a natural way to talk about it. Best to talk about vectors as vectors, right? If you get bogged down in coordinates, then everything's different, and every dimension of problem that you deal with is always going to look different. If you deal with the vectors and matrices notation, then nothing changes at all. And the fact that the shape of this matrix changes, which is automatic, given how the function is changed, will keep track of all of that for you. So, so nothing in what I have written down here would change if I change the dimension of this space, or if I change the dimension of that space, whatever. It's all automatically accounted for in the shapes of these matrices. Okay, last little quickie thing I need to, and then we'll be out of time, won't we? Okay, last little quickie thing though. Make sure to keep track of where these matrices are being evaluated. this matrix right here, DF. Oh, gosh. DF. That matrix is evaluated at A, right, at the point A, because that's where it's acting, right? That's where I am moving with velocity x prime, and I want to know what my output velocity is. So we evaluate it at A because it's acting at A. Likewise, the composition is acting at A. And so the composition is evaluated at A as well. But notice that G is not, right? G acts at that point. G just goes from the Y space to the Z space. G has never heard of A. G does not know anything about A. DG cannot be evaluated at A. It doesn't make any sense, right? DG has to be evaluated at, well, again, the point where it's acting, and it's acting at F of A. So you do have to be careful about that. If you plug in, whatever numbers you might have to do, if you have the numbers for the vector A, those numbers you cannot plug into the DG matrix. Doesn't make any sense. It's just not anyway, it just doesn't work. So heads up about that. Be careful, and we will draw the line for today right here, and we will pick up at this point on Wednesday. See y'all later. Have a good one. Hope everybody enjoyed the basketball game this weekend. I know I did.